Hello class. Today we're going to cover section 6.6, polar equations of conics. So the first thing that we're going to talk about is the eccentricity. And what that is it's the distance from the focus to a point on a conic over the distance from the directrix to a point on the conic. And that ratio is going to give us the eccentricity. And one of the interesting things about this is if it equals 1, we have a parabola. If it's less than 1, we have an ellipse. And then if it's greater than 1, what we end up with is a hyperbola. Another way to be able to find the eccentricity is also by using the ratio of the distance from the center to the focus and the distance from the center to the vertex. And that's our C and our A from the previous sections that we've used. This is going to be very, very useful. So you'll see me using this quite a bit during the examples today. Now, we have a theorem. And this theorem is pretty simple, really. What it's saying is if our directrix is on the left-hand side of our conic, we're going to end up with this formula here. And if the directrix was to be on the other side of it, if it was going to be on the right, really the only difference between the two would be that instead of having a minus in the denominator, we end up with a plus in the denominator. So it would be 1 plus e cosine theta. But I'll go ahead and show both of those examples to you so you know. But as you can see here, the distance from the directrix to our pole is a distance of p, but we see that the directrix is to the left of the pole. And since it's to the left of the pole, we're going to use the minus. If it was to the right of the pole, we would use a plus in the denominator. Let me go ahead and show you an example, and we'll go from there. So here's our example. And let me rewrite the formula so that we have it. And so this is supposed to be of the form r is equal to EP over 1 minus e cosine theta. And we can see from here that this is not in this form. And the reason we see it's not in this form is because we're supposed to have a 1 here, and instead we have a 2. And so what we need to do is divide everything by 2 on the right-hand side, top and bottom. So I'm going to get 2 over 1 minus 1/2 cosine theta. And that's the same equation as the one above. But what this allows us to see now is that our E is actually equal to 1/2. And then we also know there that E times P is equal to 2. Well, and we know that because the numerator is the 2, and we can see from the formula that EP is in the numerator. Now, we also know that E is 1/2, so 1/2 P is equal to 2, so that tells me that P is 4. Now, one of the things that's pretty neat here is since E is 1/2, we know that E is less than 1, right? So since E is equal to 1/2, E is less than 1. And since E is less than 1, we are going to have an ellipse. So the conic that we have, the conic is an ellipse. It's an ellipse. And now what we need to do is we need to go ahead and find some of our points. And so to find the vertices, what we're going to do is we're going to set our angles. And so the vertices we're going to let, to find the vertices, we're going to let theta equal 0. And we're going to let theta equal pi. And so from here, finding these two values, let me do one of them. So r is equal to 2 over 1 minus 1/2, and then cosine of 0 is 1. And so that cleans up to be 2 minus 1/2, or 4. And so we have to remember we're talking about polar, and so it's r and theta. So our radius is 4, but our theta angle is 0. So that's really a 0 angle. To find the other, we're going to go r is equal to 2 minus 1 minus 1/2. But cosine of pi is -1. And so we're going to end up with 2 over 3/2, which will then be 4/3. And so this point will be 4/3 for the radius pi. And so we can actually plot those points. So 4, 0. So here's x, here's y. 4, 0 is right here. And then the interesting thing about 4/3 is the same, it's the radius, right? It's the same as 1 1/3, and it's pi angle. So this is 0 degrees, this is pi over here. So we're actually going to be on the negative side right there. Remember the pole is our, that's the pole right there, and so that distance is 1 1/3 distance from the pole. To find the center is just going to be the midpoint between these 2 points, and so the midpoint of these 2 points is going to occur at 0, 4 pi over 3, and that's because the angle from here to here and the angle from here to here is going to yield that 0 and 4/3. So that's going to be right there. That's that is our center. This is a vertex, and this is a vertex. And so, like I said, the midpoint will be the center of the ellipse. And again, that occurs at 4 pi, comma 0. So the angle there is 0. Now, one of the things that's cool is we can actually find the distance from the center to the vertex. And so the distance from center to vertex is going to be 8 over 3. And that's pretty easy to do because my point right here for this vertex really is 4, 0, and the center right here, which I'll just write down here, is at 4/3, 0. And so to get to 4, I'd have to add 8 over 3 to 4 over 3, and that gives me that distance of 8 over 3. Now that I have my A, I can go find my C. And remember, C is going to be the distance. C is going to provide us with our distance to the focus, I believe. Okay, so let me go ahead and do this. So we remember that since E is equal to 1/2, we have E is equal to C over A. That was a formula that I gave you earlier. 1/2 is equal to C over 8 over 3. And the math that's going to come out is going to be C is equal to 4 pi over 3. And now to find our B, that's to the focus, that's C. Our B is going to be B squared is equal to A squared minus C squared, or B squared is equal to 8 over 3 squared minus 4 over 3 squared. And that's going to give me B squared is equal to 64 over 9 minus 16 over 9. And that's going to clean up to give me B is equal to plus or minus 4 radical 3 over 3. And 4 radical 3 over 3 is going to be a distance of just over 2. And it's going to be plus or minus. And so our ellipse is going to look like this. With this distance here being 4 radical 3 over 3, the distance from the center to a vertex of 8 over 3, and the distance from the center to the focus being 4 over 3. This is how we'll graph these, and just like the math said, this is an ellipse. Now, if the directrix ends up being to the right of the pole, this is the example that we end up with a plus. So this is with the directrix to the right of the pole. And the pole is always where the x and y axis cross. This is a reference table for you guys to look at. You may want to have this and write it down. So if you want, you can pause the video right now just to go ahead and look at this. But I'm about to do another example for you, and let's see if we can make connections to it. So again, we want this to be in the form where the denominator is a 1 plus or a 1 minus. So what we're going to do here is we're going to divide everything by 3. And so r is going to be 2 over 1 plus sine theta. So we can see E is 1, EP is 2, so that tells me that P is 2. And since P is equal to 2, that's very useful for us. And we can see that what we have here is a parabola, because E is equal to 1, so we have a parabola. And the focus occurs at the pole. So that's important for us to know. Now, we can find some things. So I'll do it in red. The focus is at the pole. And to go ahead and find out information on this thing, we're going to see that the vertex for this, the vertex of the parabola is at 1 comma pi over 2. And so when we go to plot that, that's going to be at 1 over pi over 2. And so that distance that we had is 1 away. And so the directrix for this thing has to be 1 away from the vertex. And so the directrix is going to occur at 2. That should be a straight line. It's kind of bad. And then the y-axis, that's known as the polar axis for this, because this is opening up or down. And we can see that the pole is happening there at pi, or the vertex is happening at pi over 2, because if I plug in pi over 2, I'm going to get 2 over 2. And then we can actually find other points, and we can use 0 and pi to find the other points. So if I go 2 over 1 plus sine of 0, that's going to be 2 over 1 plus 0, which is 2. And so remember that this is in polar, So it's 2 with an angle of 0 degrees. So that would occur here. And then if I used pi, I'd get 1 plus sine of pi. But that again is 0. So I get 0. So I'm going to get 2 and pi as my angle. In fact, since that's radians, I don't need the degree there. I shouldn't do that. And so that is this point here. And then connecting the dots, I can see that this is in fact a parabola. And it makes sense. The focus and the directrix are exactly a distance of 1 away from the vertex. And that's something that's useful for us to know. All right, let's do another example. This one's a little bit heftier, but we can do it. This is a little bit more of a lift. Now this is already in the form that we need. So we can see this is my E, so E is 3. This is my EP, so EP is equal to 3. But we also know that E is equal to 3, so that tells me that P is equal to 1. Now, since E is greater than 1, this tells me that this has to be a hyperbola, right? And so what we're going to do is we're going to try to find information for this problem again. Now, again, the pole is the focus. And so since the pole is the focus, we're going to have to go ahead and find some information. And so let's do that. So to find the vertices, we're going to do it this way. We're going to let theta equal 0 and let theta equal pi. And so the vertices, by plugging in to the equation that we have, to this equation here, we're going to get 3/4 0 and a negative 3 over 2 pi. And then the halfway distance between these two is going to be the center. And the center is 9 over 8, 0, because that's the halfway distance between those. But I'll show you guys right now what that is. So 0 3/4, and I'll do it in quarters so you guys can see. This is 1/4, 1/2, 3/4, 4/4, which is 1, 5/4, and then 6/4. Now, 3/4 0 is going to be right here. And we can see that there's a distance of 3/4 to the focus. And then the other vertices is occurring at a negative 3/2 pi. Now, pi puts us over here, but a negative 3/4 tells us to go in that direction. So that would take me to a negative 3/2, which is right here. So interestingly enough, this point here is negative 3 over 2 pi. And it's because the radius is negative, so it's going in the other direction. And then this point over here is my 3/4, 0. Okay, let me erase that because I'm going to need the space for graphing. But that's something you should know. Now, the center is at 9/8, and that's just over 1. So 9/8, that's going to occur right about there. And one of the things that we can do is, much like we've graphed in the past, we can go ahead and find our information. So C is found by its distance to the focus, right? Its distance to the focus. And so the distance to the focus, it's from center to the focus. And so therefore, I can see that c is equal to 9 over 8. So that's my c. E is equal to c over a. I know that E is 3, C is 9/8, and now we have to go get our A, which is doable. So A is equal to 9/8 divided by 3, or A is 3/8. So now we have our A and our C. Our B is going to be found by going B squared is equal to C squared minus A squared. So B squared is equal to 9 over 8 squared minus 3 over 8 squared. And then that's going to clean up to be 9 over 8. But B is going to be equal to plus or minus 3 radical 2 over 4. And that's just over 1. And so that's going to be a distance about right there and a distance of about there. And so if we remember about hyperbolas, we can make our boxes. And so I'll make the box. And then we're going to connect the corners to make our asymptotes like we did in the previous section. And now we can graph our hyperbolas that open left and right. And the thing that really gave away the whether it was opening up or down or left or right on this in this case was where the focus is. With the focus being to the left there and the center being on that axis to the right, that clearly meant that it opened up or down. If the center would have been along the y-axis, then this thing would have opened up or down. So that's just a way to do it. Okay, and then let's do this last example. And this last example is just asking us to write an equation from polar to rectangular form. And so what I'm going to do is I'm going to multiply by the denominator to both sides. So I'm going to go r times 3 minus 3 cosine theta is equal to 1. And then distributing through, I'm going to get 3r times 3r cosine theta is equal to 1. And then I'm going to isolate the 3r by itself. So I'm going to get 1 plus 3r cosine theta. And then squaring both sides, I'm going to get 3r squared is equal to 1 plus 3r cosine theta, that quantity squared. But I noticed something really actually pretty cool. And the cool thing is that r cosine theta really is x. And so this can be written as 3 plus x, that quantity squared. And then I know over here that this is going to be 9r squared. But I know that r squared really is equal to x squared plus y squared. And then I'll expand the other side. And we can actually clean up the math. And we can see the 9x squareds are going to cancel, and so I'm going to get 9y squared is equal to 1 plus 6x. And really I could divide by 9 if I wanted, which is fine, I can do that. I'll get y squared is equal to 1/9 plus 2/3 x. And this right here is a, wow, terrible. Oh, funky, but okay, whatever, I'll take it. That is a parabola. I hope you found this beneficial. As always, all the best.